Hello, you are most welcome. I'm teacher Ivan from Wunna Educational Services. I welcome you to our second lesson. We are still looking at dimensions of a physical quantity. In our first lesson, we had looked at how we derive the dimensions, or how we come up with dimensions of different quantities. We looked at dimensions of acceleration, density, pressure, among others. In our next, or in this particular video, we shall be looking at the uses of the dimensions. But before we look at the uses, we also have what we call dimensionless quantities. These are quantities with no dimensions and are described just by a number which is independent of a unit of measurement. And such quantities include strain, that is in mechanical properties of matter. You know that strain is given by the ratio of extension over original length. We have relative density, also has no units and no dimensions, simply because it is a ratio of density of a substance to the density of pure water. Relative index also has no units. Mechanical advantage, the same thing. Velocity ratio, and all constants such as pi and so on. So these dimensionless quantities have something in common. That something they share in common is that because they are ratios of the same quantities. When you look at strain, it is a ratio of length to length. Relative density is a ratio of density to density. Relative index is these are trigonometric ratios because it is sine I over sine r. Then we have mechanical advantage, a ratio of load to effort. Velocity ratio, which is a ratio of effort distance to load distance. So you notify that they are lacking units or dimensions simply because they are ratios of the same quantity. So that is the dimensionless quantities or unitless quantities. Then we come to uses of dimensions. There are two major uses of dimensions. One being that dimensions are used to check the validity of an equation, or consistency or correctness of an equation, as we shall see. Two is that dimensions can also be used to derive equations. So let us look at these two uses in two details. We shall start with the use of dimensions to check correctness or validity of any equation. So we are looking at checking the validity of an equation. When dimensions on the left hand side of the equation are equal to the dimensions on the right hand side, then the equation will be said to be dimensionally correct or consistent. For instance, we have example 1, which says that given that velocity equals to the square root of TL over m, where T is the tension, L is length, and m is mass. They want us to show that the equation is dimensionally correct or consistent. So that means that we are checking how valid is this equation. But how do we do this? In checking, we must prove that the dimensions on the left hand side are equal to the dimensions of the right hand side. So from the equation which says V equals to the square root of tension, length, and mass. So let us start with the left hand side. The dimension is of velocity V. The dimensions of velocity are given by, remember, velocity is displacement over time. So displacement is length over time. So that is per L per t. These are the dimensions on the left hand side. We also look at the dimensions on the right hand side. That is, we shall look at the square root of the dimensions of T, which is the tension, times dimensions of L over the dimensions of M. So this gives us the square root of dimensions of tension. Tension is force, and therefore it is the mass and acceleration. We saw how we derive this, times the length over mass. So we can reduce mass and mass. Then we can multiply length and length. That gives us the square root of L squared per T squared. When we multiply L times L, gives us L squared per T squared. And that gives us, square root is the same as power half. So we get L squared T power negative 2 power a half. The half affects both powers and reduces them to 1, hence giving us L per T. So L per T is our dimensions on the right hand side. And since the dimensions on the right hand side are the same as the dimensions on the left hand side, therefore that equation is dimensionally correct or valid. So that is how we show the validity of the equation using dimensions. I want us to look at one more example, and that is example 2. In example 2, we are told that the period T of a simple pendulum is given by T equals to 2 pi into the square root of L over G. They want us to show that the equation is dimensionally correct. So our equation is period T equaling to 2 pi into the square root of L over G. So since this is period T, we look at the dimensions on the left hand side. Period T is time, so it is capital T because it is a fundamental quantity. And then we look at the dimensions on the right hand side. That is, we shall have the dimensions of 2 pi times the square root of dimensions of length over the dimensions of G, which is acceleration due to gravity. That is how we shall come up with the dimensions of a constant. The dimension of a constant is 1 times L remains L since it is length, and then acceleration. This is acceleration due to gravity, which is meters per second squared, hence giving us L per T squared. This is for meters, this is for second squared. And therefore, we can cancel out this and that. And then we end up with the square root. This gives us the square root of 1 over t squared, which is also equal to the square root of t squared. When this one goes up, it loses the negative to a t squared, which gives us t. So t is the final dimension on the right hand side, and indeed it corresponds with the dimension is on the left hand side, and therefore the equation is said to be dimensionally correct or consistent. So that is how we show the correctness or validity of an equation using dimensions. Please, I want you to try out for me number 3. Number 3 show that the equation v squared equals to u squared plus 2as is dimensionally correct. And you should note that the dimensions cannot be added or subtracted, but for any equation to be added or subtracted, then it must have the same dimensions. So in our equation we have we have addition. By the time you add this and this, it means that they already have the same dimensions. Hope we've understood that. So try out that, and please, you can always comment with the answer. Otherwise, that has been our lesson. Please don't forget to subscribe, hit the bell so that you get notified whenever we have a new lesson. Otherwise, I'm Teacher Ivan from Wunna Educational Services. Bye bye. See you next time.